In this video, we're going to take a look at the concept of absolute convergence and how it differs from what we've been talking about so far when we talk about convergence. We're also going to look at two more convergence tests, the ratio test and the root test, that allow us to determine convergence of a series. But let's start with the idea of absolute convergence. We're going to be talking about absolute convergence, and in contrast to absolute convergence, we'll be talking about what is typically called conditional convergence. So what's the difference? Well, it basically boils down to this. A series defined as the sum of a sub n, and again, I'm going to leave off the subscripts here, the n equals 1 to infinity. But this series is absolutely convergent if the sum of the absolute value of a sub n converges. And a series a sub n is conditionally convergent if it is convergent but not absolutely convergent. So it still converges, but not absolutely. Okay, essentially what this boils down to is a distinction that we talked about that the alternating series test brought up. We said that for the alternating series to converge, all that's required is that the subsequent terms in the series, so negating the -1 to the n term, the thing that makes it flip signs back and forth, as long as the a sub n or b sub n of the series goes to 0, the whole thing will converge. Whereas normally, without that -1 to the n that makes the series alternate back and forth and flip signs, it's not just that the terms a sub n have to go to 0, but they have to go to 0 sufficiently quickly. And the cutoff that we've decided was they have to go faster than 1 over n. So this is essentially the distinction between absolute convergence and conditional convergence. Something's absolutely convergent if those a sub n terms go to 0 sufficiently quickly. It's conditionally convergent if they go to 0 but not quickly enough, but we're lucky enough to have an alternating series that will make the whole thing converge anyways. So this is kind of the distinction, absolute convergence versus conditional convergence. So let's look at an example of what I'm talking about. If we look at the sum from n equals 1 to infinity of -1 to the n times 1 over n. So here's our a sub n. This thing is conditionally convergent. Why? So it converges due to the alternating series test. So it converges by alternating series test because the two conditions are met. The first condition, that 1 over n plus 1 is indeed less than or equal to 1 over n. So that was that a sub n plus 1 needs to be less than or equal to a sub n. So when you increase the denominator by going to the next term, each term is subsequently smaller than the one that came before it. And secondly, the limit as n goes to infinity of 1 over n is indeed 0. So it converges by the alternating series test. However, if we look at the sum from n equals 1 to infinity of the absolute value of -1 to the n times our 1 over n, well, the absolute value just negates the -1 to the n part. No matter what, this is going to be positive. We're not switching signs anymore. So this is the same as just writing the sum from n equals 1 to infinity of 1 over n. And this thing diverges by the p-series. Oops. Because p is equal to 1. Right? And we need, in a p-series, p has to be greater than 1 in order for convergence. So p is equal to 1, which is not greater than 1, if you want to write it like that. But this is a p-series with p equals 1. That diverges. Okay, so as you can see, really the difference in this case boiled down to, do we have an alternating series or not? In an alternating series, this piece needs to go to 0. It doesn't matter how quickly. But in a series that's not alternating, this needs to go to 0, and it needs to do so sufficiently quickly, faster than 1 over n does. Some follow-ups to this are hopefully kind of self-obvious. There's a theorem in the book that states if your series is absolutely convergent, then you would also say that it is convergent or conditionally convergent, basically. So absolute convergence is the more restrictive idea. So basically, if your sum from a to n is absolutely convergent, then you can also say that it is convergent. Saying that something is convergent is a less restrictive thing than saying that it is absolutely convergent, basically. And so we can look at some more examples of things that will have this kind of effect. One of the ideas that I want to point out is one that doesn't necessarily make this -1 to the n totally explicit. So let's look at this. If we do the sum from n equals 1 to infinity of cosine of n pi over n. Well, it turns out that even though it doesn't look like it, cosine of n pi really is only two values. N is an integer, so this is just doing integer values of pi. If n is equal to 1, we're at cosine of pi, which is equal to -1. If n is equal to 2, we're at cosine of 2 pi, which is equal to +1. If n is 3, we're at cosine of 3 pi, which is back equal to -1. So cosine of n pi is either 1 or -1, depending on n. In fact, we can rewrite it as -1 to the n. Right? When n is 1, we said that was cosine of pi, which is -1. Same thing here, when n is 1, we would get -1. If n is 2, cosine of 2 pi is +1. If n is 2 here, we get -1 squared, which is +1. So cosine of n pi can be rewritten as -1 to the nth power. So we can rewrite the original series basically as, and we can rewrite the whole series as the sum from n equals 1 to infinity of -1 to the n times 1 over n. The only thing that's left behind after you factor out the cosine of n pi is a factor of 1 over n. And so this is the exact one that we just looked at a minute ago. This thing is only conditionally convergent. It is not absolutely convergent. So this thing is conditionally convergent. Okay, So there's one example. Look at another quick example. We could do the sum from n equals 1 to infinity of maybe -1. Let's make this bigger here in the middle. -1 to the n times the log of n over n. So how does that thing behave? Well, because it's alternating, all we need to check is that these terms successively get smaller as n increases and that they eventually go to 0. If both of those are true, then by the alternating series test, this thing will converge. Then we will remove the -1, take the absolute value, and check to see if just this term by itself is convergent. So, first thing is by the alternating series test, it converges, and it does. Because item 1, it turns out that the natural log of n plus 1 over n plus 1 is indeed less than or equal to natural log of n over n. This can be verified basically graphically. All we're checking is that basically the natural log of x over x, check to see if that function is an increasing function or a decreasing function. That's essentially all we're looking at. Is this function, is this piece increasing or decreasing as n increases? And it turns out it is decreasing. The numerator, the natural log of n plus 1, is increasing on top, but the bottom is also increasing. And so it's a question of which one is increasing more quickly. And it turns out natural log increases less than linearly, so less than n. The bottom is increasing faster than the top, and the overall ratio is going to go down. So this is because natural log of n increases slower than n itself. So we've got this thing, the numerator and denominator are both increasing, but if I have, there's lots of things I could have where the numerator is increasing. I could have 1, 2, 3, 4 in the numerator, and for example, in the denominator I could have this is 1 squared, and this is 2 squared, and this is 3 squared, and this is 4 squared. And what you would see is even though both the numerator is increasing and the denominator is increasing, the denominator here is just 1, down here it's 4, down here it's 9, down here it's 16. The overall set of numbers is going from 1 to a half, to a third, to a fourth. It's decreasing overall. And that's because we're comparing the top and bottom. So this is a different case, obviously. Here I'm comparing n to n squared, but here we're comparing log of n to n, and it has the same properties. But I just figured this would be easier instead of typing into a calculator what log of 1 and log of 2 and log of 3 and log of 4 are as decimals. Same idea. Okay, let me delete this real quickly. Don't need that. But the overall function itself is decreasing, and indeed the limit as n goes to infinity of the natural log of n over n is indeed 0. And this can go back to basically our hierarchy that we developed of how quickly these functions increase. So remember we had that natural log of n was much, much smaller than square root of n, which was much, much smaller than n, which was much, much smaller than n squared, right, and so on and so forth. And that's what we're looking at here. We have a function that increases in the numerator. We have another function that increases in the denominator, but the ratio is for large n, this piece is going to be way, 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 way bigger than this piece. It's going to be infinitely bigger than this piece. And that tells me that the ratio is I'm going to have something on the bottom that's infinitely bigger than the thing on the top. And that overall ratio will go to 0. So this is a really powerful tool for determining the end behavior of functions, especially when the functions involve ratios of the terms that show up here. So keep that in mind as well. Let's delete that real quickly. Okay, so we've met both of the conditions. It's an alternating series with these two conditions, therefore it converges. But we still need to check and see what happens to the term when we get rid of the -1 to the n, if we take the absolute value. So the question is the sum from n equals 1 to infinity of the natural log of n over n convergent? Right, so we have removed the alternating portion. Is this convergent? And the answer is a very strong no in this case. These terms are eventually going to 0 as n increases, but they're not going there very quickly. Right? We need them to go to 0 more quickly than 1 over n. This is going more slowly than 1 over n. If the top was just a 1, then this would be just like 1 over n. And we can compare, basically doing a direct comparison test. So in this case, we know that our a sub n here, if this is our a sub n, if we let b sub n be 1 over n, then we have the following. The natural log of n over n is definitely always larger than 1 over n, at least, again, for values of n greater than 1 here, basically starting at 1 and going up. And so basically, I guess after n equals 1, when n equals 1 exactly, right, the numerator here will be, the numerator here will be 0. But this is going to be true in general for larger values of n. And we already know that the sum from n equals 1 to infinity of 1 over n diverges by the p-series with p equal to 1. So the sum from n equals 1 to infinity of the natural log of n over n is going to diverge by the direct comparison test. And so because the alternating version up here, the alternating version with the -1 to the n converges, and the version without the -1 to the n diverges, then it turns out this thing up here is conditionally convergent. Therefore, it converges, but not absolutely. The sum from 1 to infinity of -1 to the n log of n over n is conditionally convergent, but not absolutely. Okay, so hopefully this gives you a sense. We're using these terms a lot, remembering the names, direct comparison, limit comparison. It's ultimately, long run, it's less important to know the names of these tests than just to have a general sense of when something's going to converge or not. Let's look at a couple of other tests that are going to kind of build on some of these definitions, and we can figure out exactly kind of how things are related here. So I want to start with, let me just write these out. We have two different tests. We have something called the ratio test, and a second one called the root tests. So here are the two tests that we're going to learn related to convergence. So the first one is the ratio test. And this is certainly more something that's we'll see show up occasionally. So the ratio test. Start with that one. The ratio test basically says the following. Number one, if the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. So I'm going to look at the ratio of one term, so basically one term, and then the following term in our series in the long run. If this ratio winds up giving us a constant, and that constant is less than 1, then it turns out the sum of a sub n, that series, is going to be absolutely convergent. Number 2. If we look at that same limit, so the limit as n goes to infinity of the ratio of an plus 1 over an, and it gives us an L that is greater than 1, or it diverges and goes to infinity, then in that case, the sum a sub n diverges. If, in the final case, that ratio, so the limit as n goes to infinity of the ratio of an plus 1 over an equals L, and that L is equal to 1, then it turns out the ratio test has failed us. It's inconclusive. We can't determine the answer one way or the other, and we're going to have to use a different approach to decide whether or not it's convergent or divergent. But this is important. What it's telling us is basically, do our terms, our a sub n's that we know are eventually going to 0, if this thing converges, it's because the a sub n's go to 0. Are they going to 0 quickly enough? And this is the ratio that's going to tell us if they're going to 0 quickly enough. So let's look at this in context. Let's do an example. I want to determine the convergence of the following. Let's do the sum from n equals 1 to infinity of n factorial over 5 to the n. So this is my a sub n, that term right there. So what I want to do is look at the limit. So for our ratio test, what I need to look at is the limit as n goes to infinity of the absolute value of an plus 1 over an. And so for us, what is a sub n plus 1? Well, I just need to replace the n that shows up in here with an n plus 1. So it's going to look like the limit as n goes to infinity of, on top, this term is positive. Factorial is positive, this exponential is positive, so I don't need to carry around these absolute value signs. I'll drop them. But in the numerator, I'm going to get n plus 1 factorial over 5 to the n plus 1. So that's my an plus 1 term. And I'm going to do that over a sub n itself, which we have written right there. It's n factorial over 5 to the n. And this tool is really good. The ratio test is really good when we're dealing with basically terms that involve, or when there are terms in your a sub n that involve factorial. And also with exponentials, because we get a lot of nice cancellation here. So I just need to find what this limit is. But before we do that, let's clean it up a little bit. So what I basically have is n plus 1 factorial over 5 to the n plus 1. Instead of dividing by this, I'm going to multiply by the reciprocal. So I'm going to get a 5 to the n on top and n factorial on the bottom. And now we need to think about what kind of cancellation can occur here. So if I have 5 to the n, this just means 5 multiplied by itself n times. Down here I have 5 to the n plus 1. That means 5 multiplied by itself n plus 1 times. I can cancel all but one of the 5s. So all the 5s on top will cancel with almost all the 5s on the bottom, leaving me with just this one remaining 5. So I'll come down here to a new line. I'm going to have the limit as n goes to infinity of the denominator. I'm going to be just left with a 5 as far as these two terms are concerned. So I'm going to cancel all of that with basically the n portion there, and I'll just have 5 to the first power left. And what about n plus 1 factorial divided by n plus 1? Well, think really quickly about how factorials work. So what if I had, say, 4 factorial divided by 3 factorial? That would be an example just like this. If n was equal to 3, what would I have? I'd have 4 factorial over 3 factorial. And what happens there? Well, 4 factorial is 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. And we can cancel all of the terms really nicely, and we wind up with just, in this case, the number 4. Same thing happens in general. All of the n terms will cancel, and the only one that's not going to get canceled is the n plus 1 itself. So I'm going to wind up with an n plus 1 in the numerator. Basically, this guy cancels with the factorial portion of that, and then leaves me with just the n plus 1. So I wind up with just n plus 1 on top and a 5 on the bottom. What is the limit as n goes to infinity of this thing? That thing diverges. It goes to infinity. And so that means that the whole original series that we were looking at up here, whoa, this whole series is going to diverge by the ratio test. Incidentally, we hopefully should have known that before we started this problem. Again, I gave you that hierarchy of functions. And if we look in that hierarchy of functions and try to figure out where these terms are, what we wind up having here is basically these two terms. One is an exponential, 5 to the n. The other one is a factorial, n to n factorial. They both are increasing. As n increases, both these terms go to infinity. And the question is, which one increases more quickly? And in our hierarchy, n factorial increases faster than exponentials. So factorial functions grow faster than exponentials. And that would tell me that essentially this term here isn't even necessarily decreasing over time. This term for large values of n is going to be increasing. If it's increasing, it's not going to 0, then there's no way that the sum can go to a converged value, that it can go to a single value. So hopefully you should be able to have some intuition for what behavior you expect to see. We should be able to look at this and determine divergence before you go through and formally demonstrate divergence using one of the tests that we have. So just keep that in mind. Let me give you another explanation, just maybe real quickly. This might kind of help to explain why does this work. So why does this work? Why does the ratio test work the way that it does? So let's assume that as n approaches infinity, that we do indeed get some ratio between our two values. A sub n plus 1 over a sub n does indeed go to some value L. If this is true, then it must mean that basically once you get far enough into the series, so not maybe when n is equal to 1 or 2 or 3, but if you get to large values of n, this ratio is going to get pretty close to L, right? If it's approaching it as n goes to infinity, at some point, some finite value, it's going to start to get pretty close. So what I'm saying is then if n is a large number, and let's say it's greater than or maybe equal to some capital N, at that point we're close to converge. So at that point we might say that the ratio a sub n plus 1 over a sub n, it's not equal to L, we're approaching L, we're not there, but maybe it's about L. So let's write it with approximate symbols. All this is saying is that if you sum up enough terms, if you go far enough into the series, eventually, if this ratio is indeed approaching L, eventually we'll start to get pretty close to L. That's all it's saying. Now that I have this, I'm going to rearrange these terms. I'm going to just rewrite this as the following. I'm going to multiply both sides by the absolute value of a sub n, and we'll get the absolute value of a n plus 1 is about the absolute value of a n times L. So again, all I've done is multiply both sides by the absolute value of a sub n. And doing that gives us this representation here. But if we were close to having converged after n was equal to capital N, what if we go further than that? So what if we go a little bit further than that? Let's go to a sub n plus 2. So let's say that a sub n plus 2 over a sub n plus 1. What is that ratio going to be? Well, if the previous ratio was close to L, and we've gone even further into the series, and we're eventually approaching L, we should still be very close to L. And what this is going to give me, doing the same arithmetic, is that the sum, or the absolute value of a n plus 2 is going to be about a n plus 1 times L. But I already figured out what a n plus 1 approximately is. A n plus 1 absolute value is approximately a sub n times L. So this piece is about a sub n times L squared. Right? So that's what this piece gave us. If we keep going, a n plus 3 is roughly the same as a n plus 2 times L. But I've already got an expression for a n plus 2. A n plus 2 is the absolute value of a n times L squared. And I've just simply picked up an extra factor of L, so we're up to L cubed. And again, all I'm plugging in is a n plus 3 over a n plus 2. That must be approximately L. So the whole argument here is that if this ratio has already gotten sufficiently close to L, then if we go even further down our list of values of our a sub n's, we should still be very close to L because that's the value that we are approaching. And by doing that, rearranging the terms, I can get this sequence, basically, where I can represent a n sub 1 in terms of a sub n. And then I can represent a n sub n plus 2 in terms of a n plus 1, which can in turn be represented in terms of a n in this particular manner. And a n plus 3, which can be represented in terms of a n plus 2, which could be represented in terms of a n plus 1, which could be represented in terms of a n in this particular manner. And what we see is basically a pattern that basically we're going to get a n plus k is approximately equal to, following this pattern, a n times L to the k. So if we continue this pattern on further, this is what we get as we continue to go further and further down into this series. And so these are for all the values of n greater than some capital N here. And so really that's maybe what I should be writing here is instead of lowercase n's, maybe it would have made more sense. I can come back and do this. We're only talking about values where we've sufficiently converged. So let me come back and just rewrite all of these as capital N's. That's really what they are, because we've already gotten far enough into our series that we've converged to a number close to L. Right, so this is not true in general. Hopefully these capitals are kind of readable. Again, hopefully this is semi-readable. Right, it's only true once we get to the point where the ratio is close to L. And that happens at value of little case n that's greater than or equal to capital N. And so this is what we've got. So how does this help us? Well, if we go back to the original series that looked like this, a sub n, is the sum from n equals 1 to infinity. I can rewrite that as the sum from n equals 1 up to that capital N value of those a sub n's plus the sum starting at that capital N value up to infinity of those a sub n's. So I basically just split this into two pieces. The first sum gets me up to this particular value of n, where we're sufficiently close to our ratio being close to L. And when I add up those terms, I don't know what I'm going to get, but I know that it's finite because it's a finite sum, right? I'm not going to infinity. I'm adding a finite number of numbers, and I'm going to get a finite result. This is the term that has the potential to go to infinity. I don't know what it's going to do. So is this term finite? Who knows? But I can represent this. If I start summing up all the a sub n's, starting at n equals capital N and going to infinity. Well, that's essentially what I've done here. I've got my original a sub capital N value, and then I can figure out what this an plus 1, so capital N plus 1 is, an plus 2, an plus 3. Let's sum all these up. If I sum all these up, if we look at this sum, whoa, what on earth just happened? If we sum all of these up, this piece here is going to look like, again, a sub n plus a n plus 1 plus a n plus 2 plus so on and so forth. What I'm suggesting is these terms look like these terms. In fact, I've put absolute values around these. These may be positive or negative. If they're negative or switching signs, that's even better because then maybe I can deal with an alternating series test. But worst case scenario, let's assume that they're all positive and we're dealing with the absolute values here. What that means is I'm essentially just summing up a bunch of stuff where this stuff takes on a representation that looks like this. This sum can really be rewritten as the sum from, let's call it k equals 0 to infinity of a sub, how am I doing this? K plus n. N plus k. Let's write it that way. N plus k. To be consistent. Okay, so what do I mean by this? What I'm saying is when I plug in k equals 0, I'm looking at a sub n. That's the same thing that's happening here. When I plug in n equals n, I'm looking at a sub capital N. So this sum here matches this sum here. This sum here looks like the sum of all these terms that we had over here. Exactly the same thing. What I've really got is a sum that looks like, oh, come on now. I've got an expression for this a and k. It's right here. I've got a sum that looks like the sum from n equals, oops, not n, k equals 0 to infinity of this a n plus k, which I can be rewritten as a sub n, oops, capital N, times L to the k. Whew. What is this? Well, this is just some number. Right? It just happens to be whatever the nth, capital Nth number is in the original series over here. It's just some number. And what do I have here? This is a geometric series. It converges if L is less than 1. So why is this a geometric series? Just to remind you what a geometric series looked like, you may be more familiar with the way that we wrote them before. It looked like this. Sum from n equals 1 to infinity of some a times r to the n plus 1. Essentially, that's exactly what we've got here. It's some constant times some other base raised to some power. Some constant times some base raised to some power. This thing converged whenever r was less than 1 and greater than -1 for that matter. Same thing here. This is going to converge whenever L is less than 1. So the whole thing is saying that this piece is going to be finite. It will converge whenever L is less than 1. But what was L? L was the ratio of the nth term and the n plus 1th term after you get to a certain point, after we get beyond a certain number of terms in our sum. Hopefully this makes some sense. All I did was basically find a way to say that if our ratio of the an plus 1 term and anth term is eventually going to become L after a certain point, we can use that to basically make an argument. We've got a bound here that winds up looking like a geometric series, and we know the conditions for when a geometric series converges. So basically what we did was compare our arbitrary series, the sum of a sub n, with the knowledge that eventually this ratio is going to some constant. And we were able to find a clever way to re-represent this generic series in terms of some finite series plus a portion of the infinite series that looks like a geometric series. And we know the conditions that will make this thing be finite. L needs to be less than 1. And so if this is finite and this is finite, then that means this is finite. If this is finite, it means it converged. So that's all we needed. For this to converge, this has to be finite and this has to be finite. This is finite, representing it here like a geometric series whenever L is less than 1. And that's our result. So probably way more than you needed. You don't necessarily need to use this knowledge the way that we framed it every time. Let me put that in parentheses. But this is why this ratio test winds up working. So hopefully that didn't confuse too many people. If it did, then forget about it. We have another test. Let me do the other one, the root test. The root test will allow us to deal with, so again, just to be clear, the ratio test was great. If we look back at the examples we did, the ratio test is great when we're dealing with factorials and exponentials. Ratio works great in those cases. Let me move this back over to the side here a little bit, just so I can get this formatted a little better. The root test is going to work on terms that have radicals in them. And so the root test says the following. Basically, it's also 3 parts. The first one says that if the limit as n goes to infinity of the nth root of the absolute value of a sub n, if that winds up being a constant that is less than 1, then the original sum of the a sub n's is absolutely convergent. Number 2, if the limit of this weird root, the nth root of a sub n, winds up being some constant, but that constant is greater than 1, or to be fair, it doesn't have to be a constant, it can diverge, it can go to infinity, then the sum of a sub n's diverges. And lastly, as with the ratio test, the third case is what happens if it's exactly equal to 1. If it's equal to L, which is just equal to 1, then again, the root test is inconclusive. It doesn't work. It doesn't tell us one way or the other whether the thing is convergent or divergent. So, as an example of this, I want to determine the convergence of the following. Let's save a line and write it here. Convergence of the sum from n equals 1 to infinity of 3n over n plus 1 raised to the power n. So this whole big mess is my a sub n. Well, in this case, what we need to do is look at the limit as n goes to infinity of the nth root of, in this case, the absolute value, because n is positive, starting at 1 and going up to infinity, this number in here is always going to be positive. This is always positive. The whole result's positive. We don't even need to worry about the absolute values in this case. And we're going to get simply 3n over n plus 1 raised to the nth power. And that's very convenient because we have this thing raised to the nth power. We're taking the nth root of it. Those cancel. And we just have the limit as n goes to infinity of 3n over n plus 1. What is that limit equal to? Well, it's equal to 3, right? The highest power of n on top is n to the first power, same on the bottom, n to the first power, so we just look at the ratio of their coefficients. And in this case, it turns out that ratio is 3. 3 is greater than 1. That is our L value. It is greater than 1. So our sum, specific sum, n equals 1 to infinity, 3n over n plus 1 to the nth diverges because n was greater than 1. Let's do another example. Determine convergence. And notice this is an example of one where it was kind of things that look like n to the nth. N to the nth. That's the type of problem this works well on. Determine the convergence of, let's do another one, the sum from n equals 1 to infinity of, let's do n squared plus 1 over 2n squared plus 1, whole thing raised to the nth. Hopefully this is going to be kind of obvious. Looking at this one and comparing it to this one, what's the result going to be? Well, the idea is I have this raised to the nth power, this was raised to the nth power, that gets canceled by the nth root anyways, and ultimately all that matters is what is the limit of this term without the power n up here. What is the limit of this, and is that limit less than 1? That's all this one boiled down to. What was the limit of the 3n over n plus 1, and is it less than 1 or greater than 1? In this case, it was greater than 1. What about here? Well, in this case, I'm going to get a ratio of 1/2. The highest power of n here is n squared, same in the bottom, n squared. Just look at the coefficients, I'm going to get 1/2. This thing's going to converge. And so we'll see that in just a minute. So here's my a sub n. We take the limit as n goes to infinity of the nth root of that whole mess, n squared plus 1 over 2n squared plus 1 to the nth. This nth root cancels with that nth power. We simply get the limit as n goes to infinity of n squared plus 1 over 2n squared plus 1. That ratio is simply 1/2, which is less than 1. So this bad boy converges absolutely. It converges. Whoa. Converges absolutely. Why does this one work? I'm not going to go into quite as detailed an explanation. But the idea is, if we assume that as n goes to infinity, the term raised to the nth power, so basically this piece, the stuff in the parentheses here, the stuff in the parentheses here, the term raised to the nth power is going to approach a constant. That's our assumption. If that thing approaches a constant, L, then what we have at that point we basically have, so roughly at least, something that looks like the sum from, again, after some certain point, so capital N up to infinity, we essentially just have that constant raised to the nth power. And again, it's a geometric series. That converges if L is less than 1. So that's the idea. It's basically the same argument as before. So having done all of this, I want to go back to the discussion real quickly about absolute versus conditional convergence. And then we'll wrap this up. So let me zoom in so we can read this. Absolute versus conditional convergence. Why did we care? Why did we even make a distinction? Who cares if there's two different kinds? Well, let's consider an example. Let's say that our a sub n was negative 1 to the n minus 1th power over 1 to the n. This is what we've got. This thing we already saw is conditionally convergent. It's convergent as long as that negative 1 to the n is there, negative 1 to the n minus 1 in this case. Convergent. But if I get rid of this, if I take the absolute value and just have 1 over n, that's our harmonic series, which isn't convergent, right? It's a p series with p equal to 1. It doesn't converge. But here's some interesting things. So I want to look at our sum. Our sum from our sum of a sub n. And really this is, to be fair, what was conditionally convergent. So let me erase that real quickly here. And here's why we care about this. Let's see what this thing will look like. So if I call this case 1, I want to actually write out some of the terms. So I'm going to put n equals 1 in as the first term. So a sub 1. And then we'll do the whole sum. So when I plug in n equals 1, I'm going to get negative 1 raised to the power of 0. So that's going to be 1 times 1 over 1. I just get a 1 for the first term. When I plug in n equals 2, this will become negative, and I'll have a half. So I'm going to have minus a half. Whoa, minus a half. Then the next term, I'll have a third, and it'll be back to positive. So plus a third, minus a fourth, plus a fifth, minus a sixth, and so on and so forth. So plus a seventh, minus 1/8, plus dot, 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 dot. Later on, I'll demonstrate that this is the case, but it turns out that this sum winds up giving us the natural log of 2. So just take it for granted now that that is equal to the natural log of 2. I now want to take every single term in here and multiply by a half. What does multiplying by a half do? So now I'm going to have a half minus a fourth plus a sixth minus an eighth plus 1/10 minus 1/12 plus 1/14 minus 1/16 plus dot, 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 dot. And it should be equal to half of the natural log of 2. So far so good, not too scary. What I want to do now is just kind of rearrange some of these terms in here and basically add in some zeros. So I just want to rearrange how this looks, space some stuff out, and make it look a little bit different. And I'm going to call this line 2. So line 1 was the original set that sums to equal the natural log of 2. This second set, I'm going to now space them out a little bit. So I'm going to write this as 0 plus a half plus 0 minus a fourth plus 0 plus 1/6 plus 0 minus 1/8 plus dot, 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 dot. So I've only written out the first 4 terms now because I put zeros in between every single one. Adding a bunch of zeros shouldn't make any difference. This should still be equal to 1/2 the natural log of 2. So the plus dot, dot, dot just includes these terms that I didn't happen to write. So it's the same list right here as I have right here. I've just added some extra zeros in between each term. What I'm going to do now is I want to add list 1 and 2, or I guess the two sums. So I'm going to add them together. When I add them together, I'm going to get, so let me just write them out, 1 minus a half plus a third minus a fourth plus a fifth minus a sixth plus a seventh minus an eighth plus dot dot dot. So there's that one list. That's list 1. And I'm adding it to list 2, which is 0 plus a half plus 0 minus a fourth plus 0 plus a sixth plus 0 minus an eighth plus dot 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 dot. So list 1 on top, list 2 on bottom. And that's got to be equal to, when I add up list 1 and 2 on the right sides, I have natural log of 2 plus another half of a natural log of 2. This should be equal to 3 halves times the natural log of 2. And when I come in and start to actually write this out, let's see what we get. So the first thing is, I'll notice that right here I have a minus a half and a plus a half. And those two terms are going to cancel. Over here, I have minus a fourth and minus a fourth. Those two aren't going to cancel, but they're going to combine into a negative 1/2. The positive 1/6 and negative 1/6, those two are going to cancel. And then over here, a negative 1/8 plus another negative 1/8. This is going to be a total of a negative 1/4. And so if I start combining these terms, let's see what I've got. Well, I've got this 1 plus a 0, so I've got that. There's a 1. These two terms added to 0, so plus 0. These two terms are a third. I've got minus a half. These two terms add up to a fifth. That was a 0, so plus 0. Here's a seventh. And we've got plus dot 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 dot. And this is supposed to be equal to 3 halves times the natural log of 2. But what do you notice about this list? Let's rewrite this sum. So the first term is a 1. And now I want to go in order of increasing denominators. So right now they're out of order. I'm going to now do the minus a half. So I've got 1 minus a half. I have a plus a third. What comes next? Oh, I see a minus a fourth over there on the far right. So minus a fourth plus a fifth. I should have snuck a plus in there. So plus a fifth. We'll presumably have, if we'd kept on going here, we'd have minus a 1/6 eventually. This list right here, which is supposed to be equal to 3 halves the natural log of 2, that list is the same list as the original number 1. List 1 was 1 minus a half plus a third minus a fourth plus a fifth and so on. Our new list is 1 minus a half plus a third minus a fourth plus a fifth minus a sixth and so on. The first list was equal to the natural log of 2. This new list is somehow now equal to 3 halves times the natural log of 2. This is same as list 1. But this is not the same as the natural log of 2. So what on earth does this mean? What the heck? Keep it rated PG here. So what the heck? Well, as it turns out, conditionally convergent series, even if we show that they converge, if you rearrange the terms, they converge to something different. Conditionally convergent series converge to different values if you rearrange terms. Right? We just did a little bit of manipulation. It turns out, on the other hand, absolutely convergent series only converge to a single value. Regardless of how you order the terms. So basically, it turns out that when you start to mess around with infinity and infinite series, some incredibly weird, counterintuitive things can start to happen. And that's exactly what's going on here. And it turns out the reason that we care about absolute versus conditional convergence is even if we can show that two different things are convergent, it's really only absolutely convergent series that we can trust to always converge to the same single value, regardless of how the terms in that series are reordered. If something is conditionally convergent, and S is a real number of our choosing, so we have a conditionally convergent series, exactly like the one that we've got here. This thing is conditionally convergent. We can basically pick an arrangement of all the a sub n's, so put them in a different order, to get any value of S that we want. We can rearrange to pick any value of S that we want. So we can pick a sum and rearrange terms to force this sum. That's weird. So this, again, big picture-wise, it's not going to be something that comes up a ton, but it's kind of a cool math sort of paradox here. Absolutely convergent series we can trust, conditionally convergent series not so much.